Welcome back, everyone. I would like to recap what we have done last time. Okay. So, all right. Can you please tell me what we did last time? What was the main idea?
Interference.
Interference. Yeah. Yeah. So we did interference. So that's the topic. So I'm going to recap. There's one part I wanted to go over maybe again, and then we continue. All right. Okay. So interference. So we mentioned that when you have two waves present at the same point in space, they will interfere with each other, right? And that interference can be constructive or destructive, depending on the phase between the two waves, right? And since we're talking about electromagnetic waves here, so we have the electric field part from wave 1 is E equals to the sine of K R1 minus omega T plus some intrinsic phase that may be there. This part is usually, we said, how much is this part? Usually we take it to be 0, right? And when there is this other electric field, E2 is E sine of K R2 minus omega times T 0. So these two, if the arguments of the signs are exactly the same, or they're off by 2 pi or a multiple of 2 pi, then these two will add up constructively. If one of them is a pi more or less than the other one, then they will add up destructively. The overall phase is the difference between the two arguments here. So delta phase would be the difference between the two, this minus this. And so the omegas, minus omega t minus omega t just becomes 0. So all I have here is k times R2 minus R1, which is delta R, and then plus delta P0, which is P2 minus P1, 0. So, but this is, as I mentioned, we usually take it to be 0. If it's not 0, then we would have to include it. If it is, then we just get rid of it. So if it drops, then K here is related to the wave number, and it is 2 pi divided by the wavelength. And so I get the phase, delta P, is equal to 2 pi over lambda times delta R. 2 pi, yeah. And this would be constructive if it's equal to a multiple of 2 pi times m, then we get constructive interference. If it's 2 pi times m plus a half, then we get destructive interference. Destructive interference, right? And this plus a half will make sure that you get an odd multiple of pi. And m itself, if you remember, it was 0 plus or minus, it's an integer, plus or minus 1, plus or minus 2, so on. Then we applied this concept to the interference, to the double slit interference, right? The double slit interference. So let's apply it to that, just to get the equation we got before, and continue from there. Just the double slit. Right. What was the setup? You have 2 openings, and you send light. One of them goes through the top slit, the other one goes through the bottom slit, and then you look on a screen that's kind of far away at what happens. So this is the center here, and so light is coming in from this one, and light comes in from this one. The distance between the two slits is is D. 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 The distance from here to here, we called it R, right? Called it R. Let me get my different color. So if light comes in through this slit, let's look at the middle. The one that comes in from this gets all the way here versus the one that goes from here gets all the way here. They travel the same distance, right? So delta R is 0. So in that case, it's going to be constructive interference. That middle spot would be, let's say, if it's red light, you will see a red spot. And then above it, and then you see a dark spot, and then a red spot, and then another dark spot. And you see this kind of pattern. Okay? You see this kind of pattern. In order to understand it, we said, okay, let's look at the path difference. This one travels all the way here, that's called R1. And then this one travels all the way here, that is called R2. And we looked at this one, the bottom one travels an extra distance, and an extra distance D. And what did we say that distance was? Remember? D sine theta, right? So, meaning, let's say, if this angle here is theta, let's say this is 30, then this will be 60, and therefore this one will be 30 if this is a perpendicular. So this is theta. So that means that yes, this extra distance here is D times the sine theta. And okay, so in that case, the light, both of them are in phase, so this delta phi 0 is 0. And so what remains is delta phi, this the overall phase is k times delta r, or 2 pi over lambda is equal to delta r. So for constructive, we need this for constructive. In fact, let me just say delta r in this case is equal to d times the sine of theta. Okay, d times the sine of theta. And so for constructive, interference, we need d times sine of theta, right? That's the delta r. Or 2 pi over lambda times delta r. So 2 pi over lambda times delta r to equal to 2 pi times m. 2 pi times m. You can cancel the 2 pi and you end up with d sine theta equal to m times lambda. Okay, m times lambda. And we said, okay, this is not surprising. D sine theta is the extra length traveled by the bottom one. So if the bottom one travels an extra length of, let's say, 1 lambda, then it only shifted by a lambda, which will still be, in phase, and then they will interact constructively. If it's 2 lambda, same thing. 3 lambda, same thing. So this is going to be constructive interference. For destructive, well, we will just plug in the same thing, except here you have 2 pi and then m plus a half. Then in that case, you will have d sine theta equal to m plus a half times lambda, right? M plus a half times lambda. Yeah, so an extra half wavelength, always. Okay. And then I also mentioned the hierarchy of these numbers here. I said the slit width, which you don't have to worry about right now, is A. That's much smaller than D, and D will be much smaller than the location of the spots here, which is Y, and Y is much smaller than R. So let's just write that down. So what we mean by Y is the distance from the center to whichever bright spot you're looking for. So for example, this is the 0th here. This spot here corresponds to m equal to 0, and this one corresponds to m equal to 1, and this one to m equal to 2, and this one m equal to -1 and -2. and y is the distance from the 0th one to the mth one. So let me call it ym. Okay, ym. Now ym, if you look, and now look at this triangle here, look at this triangle here, this angle is still theta, or approximately theta, because if I shift from here to here or from here to here, it's very small. You're not changing the angle by much. Okay, so so that's still theta. So y divided by this, that's opposite over adjacent. That's the tangent of theta. So notice that. Let me put it here. Notice that. First of all, I said y is much less than. D is much less than y, and y is much less than r. Okay. Notice that tangent theta is equal to y over r, and tangent theta for small theta is almost equal to the sine of theta. It's almost equal to the sine of theta. And so we can use this. We can replace sine theta by y over r and solve for y, and that will give you the direct position of the bright spots. So it would be m lambda r over d. M lambda r over d. That's the location of the bright spots. You can do the same thing here to get the location of the dark spots, and you get m plus a half times lambda times r over d. Make sure I didn't make an algebra mistake. Does that sound about right? Yes? Okay, sounds good. Okay. The next thing, remember, we also did the intensity of those bright spots. What's the intensity? And we needed to remember the intensity equation. We said the intensity is proportional to what? To the square of the electric field, right? Yeah. So you remember this. We said, we just went back all the way to EM waves. It takes just a few minutes, so let me just recall. The energy density was the electric plus the magnetic energy density, and both are had the same density, so it's just twice the electric density. And the electric energy density is equal to 1/2 epsilon naught times the electric field squared, times the electric field squared. And the electric field itself, let me put here electric field, let me put E prime squared on purpose, because E prime, let me see, E prime will be, so I have 1/2 epsilon naught, and then this E prime will be this, is E times the sine of kx minus omega t, the whole thing squared. I want to use the letter E for the amplitude, and then this one is for the electric field itself at time t. And so, and this would give 1/2 epsilon naught, and then we got E squared. Oh, I'm sorry. Did I? 2 times a half is it becomes 1, right? So there is no half here. There is no half. There is no half here. So this one here is just E squared, and then sine squared of kx minus omega times t. By the way, I put kx here. Maybe I should have put kr, because I've been using the letter r. But xr, same thing. Assuming it's moving now in the x direction. Okay. So now, but what we really need, we want the average energy. So the average energy density is, you have to average that, and when you average the sine squared, you get a half. So we had 1/2 epsilon naught E squared, right? And we said, imagine the wave is moving in space, and so it's moving across an area A. So in a time delta t, the volume it will fill is the cross-sectional area times the width. The width is the speed times time, which is the speed of the wave is c, right? So we said the energy, the average energy will be the average energy density times the volume. And the volume, I said the cross-sectional area, and then c times dt. Oh, this should say du. The amount of energy in a volume dV. Then the power, or the average power, would be du, this one is du dt, and that's equal to just the average energy density, and then A times C, right? And then we divided both sides by the area to get the intensity. So the intensity was the average power over the area. I guess it's a good exercise. And then if you divide by the area, you just get UC. And then U, the average U is this. So you have 1/2 epsilon naught times C times E squared. Now, if you forget everything, you should just remember that the intensity is proportional to the electric field squared, to the amplitude of the electric field squared. That's all. Okay, the amplitude squared. Okay. Now, what's the intensity at a particular bright spot? If you look at a bright spot, there is the electric field from the first source and the electric field from the second source. We need to add both electric fields, find the amplitude of that sum, and then put it in here, and then that's the intensity. That's what we have to do. So, here are the electric fields. Let me put it here. Here's E1, which will equal to E times K R1 minus omega times T. And then E2 will be E times K R2 minus omega times T, right? That's electric field 2. Now, I know that R2 minus R1 is equal to delta R, and that means R2 is equal to R1 plus delta R. Okay? R1 plus delta R. And I'm going to write here, wherever I see R2, I'm going to replace it by R1 plus delta R. That means E2 will equal to K. Oh, what did I forget? I have E.
Cosine.
Sine or cosine, right? Yeah, yeah. I'm going to do it slightly different today. I will still use the sine. So I think, yeah. So there should be sine here, right? Not just multiplication of these two. Sorry. So it should be sine of K R1 minus omega T, and this one should be sine also. Yeah. So let's substitute. E2 will equal to E times the sine. For R2, I'm going to replace it by R1 plus delta R. So it will be K R1 plus K times delta R. I'll put it here. Plus K times delta R. And here I have minus omega T. Or minus omega. Looks good? Okay. Let's plot these. On just the XY axis. That's too close. X, here's Y. Here. I call one alpha, the other one B. Okay, fine. Let me call sine of this. This one here, instead of I will just name it alpha. So meaning this is alpha, and this is okay. So here is this one. this has magnitude E, right? The size is E. And this part here, here is alpha. Here is alpha. So how far is this? What's this? That's the opposite of alpha, right? So E sine alpha. Yeah. So E sine of alpha. And remember what E sine alpha, alpha is all this. I just don't want to write that over and over. I'm just calling it alpha. Now the other E, the other one, this one, the E2, is alpha plus more, plus some more. So it will look like this. It also has magnitude E, it also has size E, and amplitude E, but the angle is alpha plus this, plus some more. What's that some more? It's phi, right? All right. So now I want to add them because I want to find the total electric field and find its amplitude. So if I add them, I have this one here. And I'm going to call this here EP. E at point P, at one of those points. Okay, that's EP. Okay. So if I add vectors, and I want to find the magnitude of the size of this vector, I can say, you remember if you have two vectors, let's say if you have vector C is equal to vector A plus vector B, where let's say here is vector A and here is vector B, and let's say the angle between them is phi, then C squared would be, C squared means it's the dot product with itself, would just be A squared plus B squared plus 2AB times the cosine of the angle between them, which is B. Okay. So EP squared will equal to, what's the magnitude? Our first vector has magnitude E, and the second vector also has magnitude E. So if I add them together, I would get E squared plus another E squared plus 2, and then E times E, right? First vector is E has amplitude E, and this one has amplitude E. So E squared, and then what angle do they make with each other? The yellow vector and the green one. Just look at the yellow vector, extended. Yeah, yeah. So phi, phi, yeah. Cosine. And so EP squared will be, this is 2E, factor 2E, so you get 2E squared times 1 plus cosine squared of 2, right? Then we did some trigonometry. We said cosine squared of phi will be 1/2 cosine phi over 2 minus 1, right? You remember that little trigonometry we did? Yes? Okay. So you can, where do I, so I'm saying this, cosine squared phi, I have something wrong. Can someone tell me what it is? From here to here. Almost everything is right, except one thing.
You're missing a 2 plus 2E.
The 2 is good. I factored, this is 2E squared, and this one is also E squared plus E squared, that's 2E squared.
Plus, right?
Huh?
Plus.
Plus, yeah, it is plus.
Now,
The cosine should be squared.
and between E squared and.
This shouldn't be squared. Okay. Yeah, yeah, okay, so that should not be squared. And I realized that when I wrote it here, okay? So, and then we said cosine phi is the same as cosine of 2 times phi over 2. So the cosine of twice the angle, and then you can use the double angle formula, which would say cosine squared of phi over 2 minus the sine squared of phi over 2, and then sine squared is 1 minus cosine squared, so this ends up being twice cosine squared of phi over 2 minus 1, right? Minus 1, that's what we did. So plug that in here, and you will get this. EP squared is equal to 4e squared cosine squared of 3 over 2. Okay, that's what we have. Now this makes sense. EP squared is equal to 4e squared. Think about it. If you add two things and they're parallel, so if I have e plus e, that's 2e. So 2e squared is 4e squared. It makes sense when they're parallel, when the angle between them is 0, right? So this makes sense, actually. Then we will go, here it is. The intensity is proportional to the amplitude squared. Here's the amplitude. You can substitute that. Here's the intensity. Where is it? Right here. We're going to substitute that. So the intensity, I, will equal to this. Will equal to 1/2 epsilon naught c, and then EP squared. And that's 1/2 epsilon naught c times 4 e squared, and then cosine squared phi over 2. And so this becomes 2 epsilon naught c e squared, and then cosine squared phi over 2. And we call this whole thing here, we just name it I naught. Just name that I naught. So this is, then the intensity is equal to I naught times the cosine squared phi over 2. Okay? Now we go back and substitute what phi over 2 is. Here's phi. So what's phi over 2? Well, phi is k times delta r. So we have, here is right here. K phi is equal to 1/2 phi is 1/2 k delta r, which is equal to 1/2 2 pi over lambda times delta r. But what is delta r? D sine theta, thank you. D times the sine theta, so you can cancel these, and so we'll just substitute here. So I will equal to I naught times the cosine squared of pi d sine theta over d. Okay. And hopefully I didn't make any mistakes. I think somehow I don't have pi d sine theta. Okay, good. Okay, let's see here. I think I am at the location I want to be. Does anyone have a question on this? So, looks good. So now the next topic, I wanted to do a couple of examples on the double slit experiment, but let me try to cover the next topic so that if I have time, I will go back and do the double slit experiment. Some examples. Okay. So the next topic is thin films. So let me just pause and then restart.